Hello, everyone. Thank you for being here today. I'm Sudesh, a second-year PhD student at the University of Washington, and today I'll be presenting details and measurements of a new privacy-enhancing DNS protocol called ODoH, or Oblivious DNS over HTTPS. This was a part of my internship work at Cloudflare over the last summer, and it would not have been possible without all the incredible collaborators. I'm very excited to be representing all of them in today's talk. As a quick introduction, and most of you might already know, DNS is the domain name system and is really the foundation of a human usable internet. It responds to client queries for hostnames with the corresponding IP addresses and records. And traditionally, the DNS protocol is not encrypted and it uses UDP, which continues to be a majority of the traffic that is received by the public resolver that Cloudflare operates. The usage of non-encrypted DNS leaks user information to network operators and passive network adversaries, like this detective eyeball who is observing the network, and also allows active attackers like the red monster here to modify the request from the client or the response from the resolver. To overcome some of these problems, there have been recent efforts to secure DNS using DNS over TLS, DOT, or DNS over HTTPS, or DoH, both of which have been gaining popularity and have been integrated into various web browsers and operating systems. These protocols protect the client traffic from being observed by onlookers or being intercepted and changed by an on-path attacker. But a problem still remains. The resolver operator can continue to associate the client requests to their IP addresses and build a profile around their browsing pattern. Over the past few years, we've seen active measurement research trying to understand and measure the impacts of encrypted protocols like DoH or DOT. And many large-scale measurements have shown that the performance of encrypted protocols, they vary by the choice of the resolver. It does not significantly impact page load times, and it improves user security. There have also been various attempts to improve page load times by prefetching. But while DoH did improve the security of DNS queries for the clients, it also received a lot of criticism about the small number of publicly available resolver services, essentially centralizing the internet and giving these organizations a lot of control. Additionally, these resolver operators can associate all the client queries with the client IP addresses and use the IP to geolocate their client. To maintain privacy guarantees, some operators like Cloudflare actively purge data exceeding 24 hours and give their users privacy policy-based guarantees. But bringing together organizations to agree on a common set of privacy practices to maintain user privacy requires explicit negotiation and effort. Mozilla, for example, actively defined the criteria around data retention and aggregation with frequent audits before a DoH service can be configured as a preset default in the Firefox browser. But while some users might be comfortable with a policy-driven approach, these are difficult to enforce and are really time-consuming, making users want a system that can technologically guarantee their privacy. In this talk, I'll kind of focus on the privacy critiques and the ability of the resolvers to be able to create a profile of their clients. This is exactly where Oblivious DNS over HTTPS, or ODoH, kicks in. ODoH was originally proposed as a draft at the IETF to improve client IP privacy. At a high level, there are three main components in ODoH. The first are the clients who prepare a query for which they would like a response. The goal of the clients in ODoH is to be able to successfully send encrypted messages, receive valid responses to decrypt, and in the process, be able to identify if there are malicious actors and take corrective action. The second is a proxy instance whose main role is to relay the encrypted queries and the responses to and from the targets while removing the IP addresses of the clients. The third is a target instance, which receives the encrypted query from the client, decrypts it, and obtains a DNS response for the query. The target's role is to then prepare an encrypted response and send it back to the proxy with no ability to identify the client by their IP addresses. Let's dive into the design of the ODoH protocol. At a high level, the design of ODoH is similar to that of DoH, and it kind of builds on it. In DoH, the resolver can see the client IP addresses and the query while providing secure encrypted communication channels. By injecting an intermediate proxy node, which terminates the client query and performs the query on the client's behalf, the resolver now no longer sees the IP address of the client, but the intermediate proxy sees both the client IP and the client query information. And the usage of DoH on both the client proxy and the proxy resolver segments of the connection prevent network adversaries from modifying or passively analyzing the information. But building on the proxy DoH design, we would like to ensure that the intermediate proxy not have query information and the resolver not have the client IP addresses, with the main goal of ODoH to prevent recursive resolvers and ISPs running such resolvers from being able to link clients to their queries. The security model here builds on the premise that the proxy and the targets do not collude. That's a critical part of the design. So clients need to choose proxies and targets such that they're not operated by the same entity or known to be colluding. And finally, we have the protocol where the client encrypts the DNS query using a hybrid public key encryption scheme and using a valid public key of the target resolver, and sends the query with an encapsulated symmetric key from an authenticated encryption scheme to the proxy instance. There are various ways in which the clients can learn about the services and validate them to DNSSEC validation or look for conflicting keys for the same resolvers. But in our design, we assume extended DoH adversaries, which have the ability to create, drop, and modify any messages, and also give them the ability to compromise TLS sessions in our analysis of the security of the protocol. Practically colluding adversaries on various network links who can decrypt the connection to read the message contents can create associations between the encrypted query and the encrypted response and compromise the resolver's secret key. And the compromise of the secret key could actually help such attacks. In ODoH, the proxy instance can see the IP address of the client, but not the contents of the DNS query, and forwards this message to the Oblivious target, which decrypts the query and decapsulates the symmetric key and obtains a response from the resolver. The response is encrypted by the Oblivious target using the symmetric key provided, and it is sent back to the proxy, who only sends the message to the client where it can be decrypted. In this process, the target only sees the DNS contents and not the actual client's IP addresses. And we often say that the target and resolver are independent entities, but this need not really be the case. Ideally, in practice, for performance reasons, the Oblivious target and the recursive resolver could be co-located to avoid additional network messages between the Oblivious target and the resolver. But it is still possible to maintain these as individual services without co-location, but that would incur some performance penalty due to additional network requests. We formally analyzed the protocol and proved a lemma that an adversary is unable to associate a connection between the client and the proxy with the corresponding query unless both the proxy and the targets are compromised. This brought to light a replay attack in the original proposal, which has been fixed as a part of this work. Now, with the understanding of the protocol in place, there were three main research questions that interested us. What is the impact of ODoH on the DNS response times? How does ODoH compare itself to other privacy-enhancing protocol variants that are out there today? And how does using ODoH affect page load times and user experiences? This helped us understand the cost of privacy for the user while maintaining the security guarantees that are provided by encrypted DNS protocols. For the measurements in this work, we implemented and deployed the Oblivious targets and proxies using Google Cloud and a serverless platform like Cloudflare Workers. We physically separated the Oblivious target instances from the resolvers and randomized the query from the target to three public resolvers, Cloudflare DNS, Google DNS, and Quad9, which we use in our measurements. We use 9 Google Cloud data center locations, 7 across the United States, 1 in Montreal, Canada, and 1 in Sao Paulo in Brazil, with 10 client instances running at each one of these vantage points, performing an experiment, sending DNS requests at a rate of 15 requests per minute, which is the average number of DNS requests sent by client devices with very high internet usage. The average bandwidth of all the clients running on a single core Intel Xeon processor is roughly 480 megabits per second. The clients perform DNS response time measurements by choosing pairs of available proxy and targets. And this brings us to the first result. By choosing a low latency proxy target pair for the measurements shown by the orange line, we find that the average query response time improves by 22.8% compared to only choosing the low latency proxy, which is shown by the green line. This kind of hints towards the fact that having an intermediate proxy on the same network path to the target will improve response time performance. And this path however, can be quite different from the path that a UDP-based DNS packet might actually travel on. This then brings the question of connection reuse. And connection reuse is an optimization that can enable clients to improve their performance by at least 48% at the median, avoiding unnecessary TCP and TLS handshakes for every request. But however, the reuse of connections could leak some client identity information, but it still does not leak any information about the query or their responses. And in our experimental setup, we evaluate for the worst case performance, and we incur an additional network latency between the target instance and the resolver in the architecture that we saw before. As we can see here, the target instances, which are located in Google Cloud and performing queries to 3 public open resolvers, have a faster response time for Google DNS because of potential co-location within the same data center compared to the other services. And integrating the Oblivious target into the recursive resolver can reduce the network latency to that of a cache hit for the answer and a cache miss, incurring the additional network cost to speak to the name servers. We find that co-locating these services results in better performance, and we've engineered that into the public resolver that is operated by Cloudflare as a public service for everyone. To understand the performance of ODoH, we compare this to other protocols offering similar privacy and security guarantees, and use DoH as the baseline protocol, which is shown here on the blue line on the left side, and DoH over Tor, which is a variant of DoH which provides both security and privacy guarantees in addition to some anonymity guarantees. And this is the orange line to the right side of the figure that you see here. When compared to ODoH in green, we notice that ODoH with no service co-location achieves this interesting position roughly between DoH and DoH over Tor. And the results get more interesting and better as we start to co-locate the target and the resolver together, which is shown as the purple line on this figure. And we notice that the response time for ODoH compared to that of DoH as the baseline increases at the median by 50% with the service co-location and 100% when the target and the resolver are actually not co-located. DNS protocols with message encryption like DNS Crypt tend to have much larger compute overheads and use non-encrypted channels. These protocols have higher response time and lie between the DoH and ODoH and DoH over Tor, as shown by this dotted arrow in this figure. And the performance in response times is a middle ground between baseline DoH and privacy enhancing variants such as DoH over Tor or anonymous DNS Crypt, all while achieving similar privacy guarantees. I'll keep it short for this talk, but here's a slide for reference which you could revisit for seeing the comparisons of various network architectural variants and where ODoH fits in along with the protocol security and the privacy guarantees that is offered. There's also a link to the production service, which is the case of co-located ODoH that Cloudflare operates today. This brings us to a crucial measurement that we're really interested in, the page load time impact. To do this, we establish a measurement node in a lab network connected to a commercial ISP. The node runs a local stub resolver, which is configured to use DoH or ODoH for various runs. In each run, the web browser browses to the same set of pages after purging any local cache entries and performs the page load time measurements. And we retrieve the HAR files and identify the various page events. The measurements presented here use the public ODoH services operated by Cloudflare and considers the complete page load event and DNS response times. We find that the median page load time increases by 6.7% when using DoH compared to DO53 and 9.8% when using co-located ODoH services. In summary, ODoH is a practical privacy enhancing protocol for DNS with minimal total page load time impacts, and the performance impacts of the protocol are purely network topology effects. For better usage in production systems, having an ecosystem of on-path proxies, service co-location, and connection reuse, along with the support for the protocol by clients, could be valuable for DNS privacy. Our code, libraries, and implementations are open source and are made available along with operational production services. Thank you so much.